Hello everyone, this is the video for Module 7B homework, and we're going to review the problems that are highlighted, starting with number 1. Which of the following statements is true regarding square roots? So I want to begin by talking about what a square root is, and you see two symbols in front of you, a square root symbol, and then you see x raised to the second power. The reason I have these two side by side is because they're opposites of each other. When you're working on an equation and you're trying to solve a square root, to figure out the value of the square root, you would perform the opposite operation, and in this case you would square it. So what do I mean by that? For example, if we had the square root of x equals 3, to figure out what x is, you would perform the opposite operation. Remember, the opposite of taking the square root of x would be to square x. We'll raise square to the x to the second power. And if you raise x to the second power, you must also raise everything on the right side to the second power. So you take each of the terms on both sides of the equation, raise them to the second power. The square root of x is x. When we take the square root of x to the second power, we'll get x. And 3 to the second power is 9. So our answer would be 9. That makes sense, right? Because if I plug in 9 for x, and I can punch this into my calculator, the square root of 9, I will get 3. So I'm trying to explain to you that squaring digits and taking the square root are opposites. The reason that's important is because every time you square a number, no matter what it is, like let's say that number were -2. If I raise -2 to the second power, that means -2 times -2. And -2 times -2 is +4. If I had a 5 underneath those parentheses, 5 to the second power will give you 25. So anytime you square a number, no matter whether it's a negative number or a positive number, you're going to wind up with a positive solution. Therefore, underneath your square root, it's impossible for you to have a negative number and get a real solution. So when we're looking at our answer choices here, it says the square root of a. We're trying to find the statement that's true, by the way. The square root of a is a negative square root of a, and that's not true. If we take the square root of a, we'll get the value in positive, not negative. What about the second one? The square root of negative a is a negative number. Now this directly relates to what I just talked about. It's impossible for you to have a negative square root, first of all, so you will not get a negative number. That won't be true. Now, what about number 3, letter C? The square root of a negative a is not a real number. Now that makes sense. It's impossible to have a negative square root, therefore you won't get a real number. So answer choice C would be correct. But let's look at letter D just to confirm this. I have a negative outside of the square root, and this is going to give me a positive square root solution. And that's not true because yes, the square root of a is going to be positive, but look here, we have a negative outside. So that means our final solution should be negative and not positive. So this statement is not true. The only statement that is true is letter C. Let's look at example 2. Now for each of these square root numbers, you can use a calculator. So for example 2, you can just punch in the square root of 36 into your calculator and you'll get 6. This is a good time for me to remind you that that list of perfect squares that we talked about a few modules ago will come in handy. If you did not make a list of perfect square digits, I suggest you do so. I started an example of what your list could look like here, where you just list all the digits from 1 to maybe 20 or even 30. And in the second column, you're going to square those digits. So 1 raised to the second power, 2 raised to the second power. We took 3 to the second power, right? And each time we square those digits, we'll get a list of perfect squares. So 1 raised to the second power is 1, 2 to the second power is 4, 3 to the second power is 9, and so on. The list that you acquire after squaring the digits, that's your list of perfect squares. I'm going to be referring to this list of perfect squares a lot during this module. And again, I remind you to make a list for yourself. It'll come in handy on your final exam. Let's move on to number 8. All right, so for this example, look, we not only have a number, now we have some variables underneath the square root. When it comes to variables, notate this information. Taking the square root of x squared is going to give us x. Remember we said squaring a digit is the opposite of squaring it, of taking a square root. So squaring it is the opposite of taking the square root. Therefore, if I take the square root of x squared, I'll get x. No matter what x is. So x could be some other variable. It could be the square root of k squared. That would mean I get k. So whichever variable you have underneath your square root, the goal is to look for sets of 2. So I have this in note. I'd like you to add this to your notes. You're looking for sets of 2. How many sets of 2 are there underneath your square root? Now that's going to come in handy for number 8 and moving forward because we have variables that we're dealing with. We got a to the 15th power. Now the number we don't have to really be concerned about because 81 is a perfect square digit. The square root of 81 is just 9. However, when it comes to a to the 15th power, remember we're looking for sets of 2. So I'm going to break down this a to the 15th power using sets of 2. How many sets of 2 can I get from a to the 15th power? So I'm going to figure this out just by combining a bunch of sets of 2's. So I got a to the second power, a to the second power. That's 2 times 2, that's 4. I can keep going. A to the second power, again, a to the second power, a to the second power. All right, we're looking at a 15. I'm trying to see how many sets of 2 can I get out of here. If I divide this by 2, how many sets of 2 would I get? So that 2, 4, 6, 8, 10 of them, which means there are 5 left. And within that 5, I have 2 more sets of 2, right? There's 4 more. So that's 1, 2, 3, 4, 5, 6, 7 sets of 2. 7 times 2 gives us 14. And that means I'm going to have 1 A left over. These sets of 2's, the 7 sets of 2, that's like me taking the square root of each a squared. And remember, when we take the square root of a term to the second power, it's just going to be that variable. So the square root of this a squared is just going to be a. The second one would be a. The third one would be a. The fourth one would be another a. The fifth one, the sixth one, and the 7th one. That's just us taking the square root of each of these a squares. And then remember we have this one left over. But all of these a terms that we've taken the square root of, I can combine these. They each have a variable of 1. So I add all those variables of 1. I wind up with a to the 7th power. If I take the square root of all of these a's, which will give us a to the 14th power, by the way, right? I'm just dividing this by 2. That will give us a to the 7th power. So a to the 7th power, and what we have to leave underneath the square root is that single a by itself. So when I take a to the 15th power, take the square root of that term, I'm dividing, I'm trying to see how many sets of 2 I can acquire from a to the 15th, and I can acquire 7 sets of 2. So the square root of those 7 sets of 2 would be a to the 7th power. 9 came from 81. Remember 81, we took the square root of 81. What's left underneath your square root is a. So our answer for number 8 will be 9a to the 7th power times the square root of a. Let's look at number 9. Now for number 9, you have 2 variables. You have the square root of a to the 8th power times b to the 2nd power. We're looking for sets of 2. So when I look at a to the 8th power, how many sets of 2 are there in 8? There are 4 of them. So the square root of a to the 8th power will be a to the 4th power. When I look at my b term, how many sets of 2 are there in b squared? There's just 1. So b to the 1st power, just b by itself will be the square root of b squared. And this will be your solution, a to the 4th power times b. Now let's move on to number 14 or number 15. I have a note here for you. When you're dividing, right, remember that you want to pay attention to those lists of perfect square digits, because in order to simplify these problems, you're going to divide by the largest perfect square digit. So the number that you're looking for the biggest perfect square that can be divided into each of these. First of all, by us seeing this long square root over 27 and 4, this is equivalent to the square root of 27 over the square root of 4. We can separate that square root symbol. And let's just take the square root of the numerator and the denominator. In the numerator, the square root of 27, if you go punch in the square root of 27 into your calculator, you will get a decimal. That means you have to now figure out what is your largest perfect square digit, referring to this note, that can be divided into 27. So you just go down your list. Remember your list of perfect square digits, 2, 4, 9, 16, and see which of these digits can be divided evenly into 27. And the largest one would be 9. So 9 can be divided into 27. How many times? What do I multiply 9 by in order to get 27? It's 3. So I can simplify this underneath the square root 27 using my largest perfect square digit, 9 times 3. Now let's keep going in the numerator. We now know what the square root of 9 is because it's a perfect square. So I can take that square root of 9 out from underneath the square root. Symbol. So the square root of 9 is 3. You see how we have the 3 that's still underneath the square root symbol? You keep it there. Now in the denominator, the square root of 4 is a perfect square digit. That just gives you 2. So we keep 2 in the denominator, and this is our solution. 3 square root 3 divided by 2. All right, let's move on to number 19 and 20, which both deal with the Pythagorean theorem. So I wrote some notes here to remind you of what the Pythagorean theorem is. It refers only to the sides of right triangles. So we have this example of a right triangle here. This box indicates a 90-degree angle. That's your right angle. The hypotenuse, HYP, stands for hypotenuse. That's the side that's across from the right angle. The other 2 sides of the triangle are called your legs. So we use these digits in order to find missing pieces of right triangles. The formula for Pythagorean theorem is a squared plus b squared equals c squared, where a and b are the legs of the triangle and c is the hypotenuse. Look at our example. We have 20 across from our right angle. Therefore, 20 is going to be the hypotenuse. And remember, the other 2 sides are just your legs. So this would be a leg, and 10 would be a leg. The side that has no number or letter, I'll just replace letter X. You can use any variable that you want. Now we're going to substitute those values into the Pythagorean theorem. So we're using our formula for Pythagorean theorem, a squared plus b squared equals c squared. Remember, c is your hypotenuse. In our case, the hypotenuse is 20. So we'll replace c with 20. That's 20 to the 2nd power. Now for a and b, we're replacing 10 and x. So we'll have 10 to the 2nd power plus x to the 2nd power. And then we're going to simplify this by squaring each of these terms. So 10 squared would be 100 plus x squared equals 20 to the 2nd power, or 400. Now we need to solve this equation. So we're going to subtract 100 from both sides of the equation. Cancels out. We'll bring down the x squared on the left side of the equal sign. That's equal to 400 minus 100, or 300. Now we aren't done. Remember, to solve this, we're going to take the opposite of squaring a number, and the opposite of squaring a number is the square root. Our directions tell us to give an exact answer and a 2 decimal space approximation. So you should have 2 solutions here. To get the exact answer, we're going to find the largest perfect square digit that we can divide into 300. And so we're on this part of our solution. The largest perfect square digit that we can divide into 300 would be 100. 100 times 3 gives us 300. And because 100 is a perfect square digit, we can take the square root of that. We can move it outside of the square root symbol. It'll be 10 outside, and then times the square root of 3. So for the exact solution, the first part of this particular problem, you're going to put 10 square root 3. Now when it comes to us getting our approximation, our 2 decimal approximation, we're going to refer to our calculators. So in your calculators, you simply just want to take the square root of 300. Punch in square root 300. When you punch in square root 300 into your calculators, you'll get a decimal. Your decimal will be a little bit longer than what you require here. You're only required to go 2 spaces after the decimal point. So you're going to see 17.32050.8. Now we're only required to go 2 places. So 17.32 is how we round here, since that's 0 behind the 2. The second part of this particular problem we write as 17.32. All right, now let's look at number 20. For number 20, you don't have to do both parts. You only have to find the missing piece of the right triangle. So we're looking for this side. And then you're asked to find that length, and we're going to round 1 decimal place. So using Pythagorean theorem again. How do we know we're using Pythagorean theorem? Look, we have our right triangle shaped out here for ourselves. This is our 90-degree angle. The side that's across from the 90-degree angle is x. So this is our hypotenuse. Let's use the Pythagorean theorem again. A squared plus b squared equals c squared. We just determined that our hypotenuse is x. It's the unknown value. So we'll replace c with x. And the legs are 22 and 4. And it doesn't matter what order you write the legs in. So 4 squared plus 22 squared, or you can write them as 22 squared plus 4 squared. All right, now let's simplify this. We want to square each of these terms. 4 squared, we would get 16. We want to keep going. 22 squared will give us 484 equals x to the second power, or x squared. Now add the 2 terms on the left side. 16 plus 484, we get 500 is equal to x squared. Now at this point, the opposite of squaring a number, in order to solve this equation, you have to perform the opposite operation, is taking the square root. So x is equal to the square root of 500. We just punch that into our calculators, and we want to round 1 space after the decimal point. So when you punch in the square root of 500 into your calculators, you should get 22.360, and we only rounding 1 place, so we should round it as 22.3. All right, let's move on to number 23. For 23, you're asked to add or subtract as indicated. I'm writing a note here to remind you, when you're adding and subtracting, we're really just combining like terms. I have 2 square root 5 plus 6 square root 5. minus 5 square root 5 minus 5. Now, which terms look alike? All of these terms with the square root 5s on them. That means we can combine them. I have 2 square root 5s plus 6 square root 5. 2 square root 5s plus 6 square root 5s will give you 8 square root 5. Add these first two terms together. And now let's just write the remainder of the problem. Behind that 6 square root 5, we have minus 5 square root 5. So minus 5 square root 5, and then minus 5 on the end. We still have these two terms that can be combined. We have 8 square root 5s minus 5 square root 5s. That'll give you 3 square root 5s minus 5. And we stop here. That's your solution. Since 5 doesn't have a square root 5 at the end of it, you can't attach it to the 3 square root 5. All right, let's look at number 27, which is the same concept as the previous problem. I have 3 plus 7 square root 5, 3 plus 7 square root 5 minus 5. Now, which terms are alike? My 3 and my minus 5. So I write this as 7 square root 5, since there's no other square root 5 terms to combine here. And then 3 minus 5 is negative 2. That's your solution. Let's look at number 28. Here's a note here that you want to multiply. So we're going to multiply these terms that are underneath the square root, and then we're going to divide by the largest perfect square digit. So let's multiply first. I have the square root of 27 times the square root of 3. When I multiply those two terms together, we get the square root of 81. And the square root of 81 is 9. That's your solution. All right, let's look at number 31. We're going to multiply and assume that each of these variables are positive. So underneath my square root, I have 11z times the square root of 11z. Now, when I multiply these two numbers together, 11 times 11, I'll get the square root of 121. When I multiply z times z, I get z to the second power. So taking the square root of 121, that's a perfect square digit. The perfect square you would get is 11. Now z to the second power, again, that's a perfect square. The square root of any term to the second power, remember, is just going to be that term. So that'll just be z. That's our answer, 11z. What do you notice here? When I square a digit, right, when it has the same square root term, I'm going to wind up with just whatever that term is underneath the square root. For example, if we had the square root of 50 times the square root of 50, we get 50 without the square root symbol. If we had 10k to the second power, square root of this term, times 10k to the second power, we'll get 10k to the second power without the square root. And the powers don't always have to be even either. So if we had m to the 5th power, the square root of m to the 5th power times the square root of m to the 5th power, we'll wind up with m to the 5th power without the square root symbol. So just remember, squaring a square root just gives you that term without the square root symbol. That comes in handy when you're working on larger problems. For example, 34, you have the square root of 34 outside of parentheses, so you need to distribute. We're multiplying 14 times 2 and then 14 times 7 in order to get our square root of 28. 14 times 2 gives us 28, plus 14 times 7 gives us 98. Now, if you punch in the square root of 28, you'll get a decimal. If you punch in the square root of 98, you'll get another decimal. Therefore, we got to find the largest perfect square digit. Look at your list of perfect squares. So 2, 4, 6, or 2, 4, 9, 16. You want to look at your perfect squares and see which is the largest that you can divide into 28 and 98. Now, when we look at 28, the largest perfect square digit we can divide into 28 is 4. So we simplify this using 4 times 7. When we look at 98, the largest perfect square digit that we can divide into 98 is 49. 49 times 2 would give us 98. Now, we know the square root of 4, so we can pull out the square root of 4, which is 2. So that'll be 2 square root 7 for the first term. We know the square root of 49, so we can pull out the square root of 49, which is 7 times square root 2. We keep the square root of 2 inside. This is our solution. We have 2 square root 7 plus 7 square root 2. All right, let's look at number 37. Now, when you're asked to divide these square root problems, you have to do what's called rationalize the denominator. We need to remove those square root symbols from the denominator in order to simplify this problem. Now, the only way I can get rid of this square root symbol, remember, if we multiply another square root that is the same as the square root, we would wind up with that term by itself without the square root symbol. The square root of 7 times the square root of 7 gives us the square root of 49. But what is the square root of 49? It's 7. So this is how we rationalize the denominator and remove this square root symbol from the denominator. But whatever you do to the bottom, whatever you perform in the denominator, you must also do that same step to the numerator. So we also have to multiply 525 in this case times 7. And we'll get the square root of 3,675. And we need to simplify this term. We got to find the biggest square root that we can divide into 3,675. And the largest perfect square digit that can be divided into 3,675 is 1,225. Now, 1,225 times 3 would give us 3,675. In our denominator, we keep 7. Now, we know the square root of 1,225, so we can pull that out. The square root of 1,225 is 35. We keep the 3 underneath the square root symbol, carry over our 7. Now notice here we got 35 over 7. 7 can be divided evenly into 35. It goes 7 times. Our final answer would be 7 square root 3. 7 square root 3. All right, now let's look at 41. We're rationalizing the denominator again, which means we have to multiply by that term in the denominator. So we're multiplying by the square root of 10y, both the numerator and the denominator by the square root of 10y. And then the square root of 10y times the square root of 10y would just give us 10y without our square root symbol. And 1 times the square root of 10y. So 1 times the square root of 10y would give us the square root of 10y. This is our solution. We can't simplify that any further. And this is the last problem from Module 7B homework.